In this video, we're going to introduce you to the basics of similarity, including a lot of vocabulary terms and symbols that we use. So when we talk about similar, we also have to kind of compare that to congruent. So we also want to show you the symbols, the markings that are used to indicate that. This is the same tilde that you would use in Spanish over the N in the ñ, and congruent has that same tilde but with an equal sign underneath. If a shape is similar, that means that you have the same shape but in a different size. That's the kind of informal way of describing it. When we say same shape, we mean specifically not just that you're looking at two octagons, but all of the corresponding angles are the same in those octagons. And when we talk about different size, specifically, we're talking about the corresponding side lengths are proportional. Now, if you notice in both of those, I mentioned the word corresponding. If you're not familiar with the word corresponding, some synonyms for that would be matching or in the same location. So when I look at congruent, also same shape, right? All of the corresponding angles are the same, but a congruent shape has the same size. So all of those corresponding side lengths are the same. Notice I inserted the word corresponding when I read this out loud. When I say all side lengths are the same, I don't mean that we're looking at a square where every side length in a particular shape is the same, but all of the corresponding side lengths, all of the matching side lengths in the same positions from those two figures are the same. So here you have exact copies. Here you're looking at something that has either been enlarged or shrunk down to create a similar copy but in a different size. Speaking of copies, a lot of times when you're talking about similar figures, you might also be talking about making a dilation. That's just a mathematical term for changing the size. In this case, we've not only changed the size, we've also flipped it over, but you can handle that. If I have an original shape that undergoes a dilation, the new shape is called the image. And if I want to use the same letters that I've originally identified my vertices with, then I need to then add these single quotes, right, here next to each one, and that's read as A prime. That just means this is the vertex that is the copy of vertex A in the original, right? So here we have trapezoid A, B, C, D. Here we have trapezoid A prime, B prime, C prime, D prime. And by using those repeated letters, it helps us better match up which vertex and which side over here corresponds with each side over here, right? AB corresponds with A prime, B prime. Even though this shape has been turned, this helps us keep everything matched up. Now, take a look at this pair of shapes at the bottom. Sorry, let's ignore that green. I've got two triangles. Notice again, they're not turned the same way, and I didn't label the vertices this time. We're going to have to pay attention to other clues to figure out if these are similar. Our definition of similar says that we have to have the same shape where all of the angles are the same, but different size, meaning that the corresponding side lengths are proportional. So if I take a look, first I need to see, do I have all of the angles that are the same? Well, I've got some matching right angles, and then these markings indicate that these angles are the same. Here I used 2, those indicate that those markings are the same angle measure. So yes, I have all angles are the same, right? 2 right angles, whatever this angle measure is, it's the same here. Whatever this angle measure is, it's the same here. Now I need to see if my side lengths are proportional. Basically, can I create equivalent ratios from all of my corresponding side lengths? Well, let's start with our shortest side length between the right angle and the single little curve here. So I can either say 6 over 3 or 3 over 6. I have a feeling we kind of like to keep our fractions with the smaller number on top if we can. So small on top of big gives me 3 over 6. What does that reduce to? That reduces to 1/2. Well, all of my other ratios of my side lengths reduce to 1/2. Well, so now let's go to our middle side length between the right angle and the double curve here and here. So 4 over 8, yes, sure does. That reduces to 1/2. And then finally, the hypotenuse of our right triangles, remember the side across from the right angle, And I still notice every single time I put the small one on top of the large one to be consistent, that also reduces to 1/2. So my corresponding side lengths are proportional. I could take any of these two ratios of my side lengths and create a proportion, a comparison of two equal fractions from them. So are these figures similar? Yes, they are. Everything matches up. When I'm creating these ratios of corresponding side lengths, I am creating the scale factor, right? Scale factor, by definition, is the ratio of two corresponding side lengths in similar figures. Now, you probably think of it as maybe it's the multiplier, it's how many times bigger the figure has gotten. Those are some informal ways of describing it, but this is the technical definition. Please write that down. Now, in case it's not obvious, your scale factor will be some number bigger than 1 if you're going from a small to a large figure. So if I start here and I'm applying a scale factor to create this larger figure, it's only going to happen if my scale factor is bigger than 1. So let's figure out what that scale factor is. I need the ratio of the corresponding side lengths. Now, without marking it, I think we can see our small side lengths match up, our large side lengths match up. So these would be the ratios of the corresponding side lengths in this case. Notice, if I'm going from a small to a large figure, right, my original value goes in the denominator, just like when we were doing percent of change. So maybe that's going to help you. The original value goes in the denominator. The values from the image are here in my numerator. What do these ratios reduce to? Because I definitely want to reduce. Well, actually, this is the simplified version of this fraction. If you wanted to, you could change 5/2 into a decimal, but there's no need to. So your scale factor here is 5/2. If you really wanted to change that to 2.5, you can also do that. Please don't ever leave a decimal in the middle of a fraction, right? If this was the only ratio of side lengths you have, you would need to maybe multiply both numbers times 10 and then simplify from there. Use one of the tricks we've talked about previously. Don't leave decimals in fractions. However, if my figure is going from a large to a small figure, my scale factor is going to be less than 1. Right? So here I've got a couple of triangles, and speaking of markings, notice these single hash marks in all of these. Actually, I probably should have kind of double hash marks here, because just like with the curves and the angles, these markings mean all of these are equivalent to each other. These are all equivalent to each other, but not equal to these. So that's why it was better to put double hash marks in each of those side lengths there. So I have an equilateral triangle in both cases. It goes from a side length of 12 to a side length of 3. So if I want to know the scale factor from here to here, remember my original actually goes in the denominator. So once that simplifies, I see that 1/4 is my scale factor. Time for you to try something on your own here. You've got figure 1 and figure 2. That's what FIG is abbreviating, figure 1 and figure 2. And I'm telling you these figures are similar. So use that information to answer these questions. In order to find the scale factor, I have to find a pair of corresponding sides where I know both of the side lengths. If I look and I start to use 6, I'm not going to be able to figure out the scale factor because its corresponding side length is the x, and I don't know that yet. However, 15 and 10, the longer sides of these parallelograms, are both there, so I can use those values. So to find the scale factor from figure 1 to figure 2, I would need to put my original in the denominator. 10 is going to go match up with that, and 10 over 15 reduces to 2/3. Now for part B, from figure 2 to figure 1, right, my shape is getting larger, so I know this time it's going to have to work out to be bigger than 1. Let's take a look at what that would work out to be. I would just put the 10 in the denominator this time, since that would be my original from figure 2 to figure 1, means figure 2 is my original, and the 10 goes down here. And when I do that, I get 3/2 as my scale factor. Notice the answers are reciprocals from each other. They should always work out to be that way when you find the two different scale factors between any pair of matching similar figures. for this very reason. All that you're doing is changing which value goes in the numerator and which one goes in the denominator, so your scale factors should always be reciprocals of each other. Last but not least, we need to find the value of x. So I can take that pair of corresponding side lengths, or its reduced version, that scale factor, and use it to make a proportion to find x. I know x matches with 6. So x matches with 6. Now I need to create an equivalent ratio on the other side, and I can do 10 with 15. If you'd rather use the reduced version of 2 over 3, no problem. I think it's pretty easy to see here how to figure out what x is going to be. 3 times 2 is 6. 2 times 2 tells us that x equals 4. Don't forget your units, 4 centimeters. Another important aspect to pay attention to when you're looking at similar figures is how does scale factor affect the area and perimeter of those similar figures. So here's an example. I'm letting you know A is similar to B, and I've drawn this out. Now I've also labeled all of my side lengths. Oh, and again, I should have had double hash marks over here to show that these are all equal to each other, not equal to this. These are all equal to each other, these are all equal to each other. And I know that they've got some type of scale factor going on because they're similar figures. Well, so what is the scale factor, right? From 2 meters to 6 meters, I think we can pretty easily tell the scale factor is 3. Let's take a look at the perimeter. What's the perimeter of A? It's a square, right? So it should be pretty easy to calculate that that's 8 meters. How about the perimeter of B? Did you figure out that it was 24 meters already? How many times larger is our scale factor, is our perimeter of square B compared to square A? It's 3 times larger. Notice that 3 is the same 3 of our scale factor. Is that relationship going to be true when we compare their areas? Let's take a look. So what is the area of square A? It's a square, so 2 times 2 is 4 square meters. How about the area of square B? 36 square meters this time. Wait a minute, 4 times 3 doesn't give us 36. How many times larger has this area gotten compared to this? It's 9 times larger. That's not the same value anymore. But it makes sense if you start to think about what happens when you apply a scale factor to the individual side lengths. And to help visualize that, I want you to consider this question. How many square feet are in 1 square yard? I've drawn a square here. It's 1 yard on each side, so that's 1 square yard. But how many square feet are in that square yard? Well, that means I have to look at how many feet are in each side length. If this is 1 yard long, right, that means it's actually 3 feet long. And if this is 1 yard high, again, that means it's 3 feet high. So I can't say, while 3 feet does equal 1 yard, it's not 3 square feet equals 1 square yard, right? Look what happens. 9 square feet equals 1 square yard. The same thing is happening up here, right? Because this side length has been multiplied by 3 and this height has been multiplied by 3, the overall effect to the area is that it's been multiplied by 3 twice. It's been multiplied by 3 squared. That's why the area gets 9 times bigger. So to recap, perimeter is multiplied by the same scale factor as the side lengths, but the area is multiplied by the scale factor squared. Here are some hexagons. And, oh, again, I need to be putting my double markings. So this is a regular hexagon, this is a regular hexagon. I'm letting you know that they are similar. And that the area of hexagon A here is 9 square centimeters. Now I want to find the area of hexagon B. Well, do you know a formula for the area of a hexagon? I know one, but it's kind of complicated, and I certainly don't want to do all of that math. I can instead just use the fact that these are similar figures in order to find the area of hexagon B. In order to do that, I need to find the scale factor. What's the scale factor between these two hexagons? From A to B, we would have to have a scale factor of 4. So to find the area of hexagon B, I need to take the area of hexagon A and multiply it by my scale factor squared. Even though we're not applying length and width here, area is a two-dimensional measurement. So both dimensions have been multiplied by 4. The overall effect to the area is that it's multiplied by 4 squared. So what does that work out to be? Well, exponents come first, so 4 squared is 16, and 9 times 16 is 144. The area of hexagon B is 144 square centimeters. Let's think about how the perimeters are going to compare. How will the perimeter of A compare to the perimeter of B? So you have to pay close attention to the wording here. How does A's perimeter compare to B's perimeter? So now we need to go the opposite direction. What's the scale factor from B to A? Remember, it's got to be the reciprocal. So going this direction, the scale factor is going to be 1/4 as opposed to going this direction. So how does the perimeter compare? The perimeter is also 1/4 of the size of B's perimeter. All right, last do now problem. I don't know if you remember those original and image trapezoids from our first page, but they're back. And this time I'm letting you know that the original trapezoid was dilated by a scale factor of 1/2 to create this image trapezoid. All right, so again, I'm going to need some scale factors, and I'm going to have to pay attention to which direction they apply. So they tell us that this original had a scale factor of 1/2 applied to it to create this image. So if this original perimeter was 13, that perimeter would be multiplied by the same scale factor of 1/2, and that means I would just do 13 times 1/2 to give us 6.5 inches as the perimeter of my image trapezoid. That's pretty simple, but letter B gets a little bit trickier. This time we're starting with the image, and I'm telling you that the area of this image is 5 square inches. Now I want to go back to find the area of the original. That means I need to find the scale factor going in reverse. It's going to be the reciprocal of the given scale factor. So the scale factor going in reverse is going to be 2. Even more than that, I need to remember that area is multiplied by scale factor squared. So that image area of 5 square inches multiplied by the scale factor squared tells me that the area of the original is 20 square inches.